All right, so we are going to consider the complete spectrum of 4-bromo 2-pentanone. Obviously, the first thing that we need to be able to do well is to draw the structure. So the way that I would advise you all to draw it is to draw the skeleton first. You know that you're going to have 5 carbons in an uninterrupted chain. Off of carbon 2, there will be a carbonyl because it's a ketone. And off of carbon 4, there will be a bromine atom. And on this structure, I want you to consider several things. What will the IR look like in terms of obvious peaks? What spectral characteristics of the mass spectrum will appear? What about the proton NMR? Especially with regards to the number of peaks and the splitting. Now, of course, if you know chemical shift data, that's fine, but if you recall from class, I put a very large emphasis on number of peaks and splitting. And of course, we can talk about the carbon NMR spectrum as well. So if we look at the structure of this molecule, let's begin to predict what we would find on the IR and on the mass spec. So on the FTIR, we would anticipate a carbon-oxygen double bond stretch between 1650 and 1780. Now, I will tell you that very rarely will you see something as energetic as 1780. Normally, the range is 1650 to 1740. 1740 would correspond to esters, 1650 to a polyconjugated carbonyl. The mass spec. Rather than, we know we have a bromine atom, so we would see an M and an M plus 2 that is nearly 50-50. Remember that the M is just a little bit larger than the M plus 2, so it's about 51% to 49%. But rather than estimating this, I'd rather show this to you, and this also illustrates what a nice drawing program ChemDoodle is. So what I'm going to do on ChemDoodle, as I open this up, I'll simply draw the structure, and we'll look at the molecular ion. Boy, too much coffee already. Okay, so the way this works is pretty slick. So I'll draw the structure. I know y'all are just mesmerized by this right here.
It's kind of neat.
Now I'll go to spectrum, generate mass parent peak. And I'm just going to shift this over. And this is what we see. We see that we have a molecular ion peak at 164. Now we do have an M plus 1, and we could use that information to find the number of carbons if we have more specific mathematical data. And then at 166, we see a nearly equal intense M plus 2 peak. So once again, we're talking about 4-bromo 2-pentanone. And now we're looking at the number of hydrogen environments. So the terminal methyl group where the carbon is alpha to the carbonyl is certainly one environment. I'm going to render those in magenta. You know, if a guy knows a color like magenta, there's only 2 possibilities. You're either married or you're gay. For the record, I'm married. That's just not the kind of knowledge you get everywhere, James.
I know.
That's what I bring to the table.
Yes, I wouldn't care what magenta is anyway.
Someday you will. Or you're going to be a very lonely, lonely man.
There are ways to rectify that with money.
So we have 4 environments. Now let's talk about how these will split. So let's start with the magenta category where you have 3, and I'm not sure why I cannot go in alphabetical order. These should all be HA, and these should be both HB. So environment HA is not within 3 bonds of another hydrogen. So the closest one would be 1, 2, 3, 4 bonds. Remember that we can't split a signal unless we have an NMR active nucleus within 3 bonds of our hydrogen of interest. So HA will appear as a singlet. Boy, that is really crappy looking.
Double bonded oxygen, right?
Yeah, I'm going to show you this in just a couple of minutes.
Just make sure we're ordering it properly.
You really got to learn to have a steady hand with this. I know this looks like it's easy, but imagine drawing on something and nothing appears where you're drawing, and you're looking at the screen while you're writing. I have very limited mechanical skills anyway, so this is really pushing me to the limit. So HA should be a singlet. And what I'm going to do for y'all is I'll do the structure on the chem doodle again, and we'll see what that one looks like, and then we'll also try to look up an experimental spectrum for it as well. All right, so HB in red is within 3 hydrogens of HC, and there's only 1. That means HB will be a doublet. And these 2 peaks are both alpha to a carbonyl. I do believe that the red peak will be a little further downfield than the pink or magenta peak. So remember that our delta value, you have 0 here. This would be at about 2.2. This is probably at about 2.6. Remember, the chemical shift values is not the major area of concern right now. It is the number of proton environments and the splitting. Those are the 2 big ones. All right, so for HC, it can be split into a triplet from HB and into a quadruplet from HD. That's going to be 12 peaks, so it's going to be a multiplet. And probably it's going to appear as 6 peaks on the NMR. So something like this. And then, of course, HD is going to be split by HC, and that's going to appear as a doublet as well. So of our 4 proton environments, these are the splittings. Let's take a look at what ChemDoodle predicts for the proton spectrum. So all we really want to do is highlight our molecule. Let's get rid of the mass spec. Highlight our molecule, go to Spectrum, generate Proton Nmr. First of all, we see 4 peaks. And I'm going to stretch this out here to just get a little bit better resolution. Now look at what we see. We see a multiplet, a doublet, a singlet, and a doublet. Okay? Now, let's compare this to what we have. Multiplet, doublet, single, doublet. The biggest difference is we have our multiplet here, whereas they have it all the way over here. Again, the chemical shift is the least important of all of the factors to consider because you got competing effects. Is it going to be more deshielded when it's close to bromine or more deshielded when it's close to the carbonyl? The answer appears to be when it's closer to the bromine. That's not something I would have anticipated. Also, you got this hydrogen that is alpha to the bromine, but it's gamma to the carbonyl, so there's still an effect. So our predictions are validated by this theoretical NMR. So we've now discussed IR, mass spec, NMR with regards to the number of proton environments and to the splitting. What about the carbon NMR? How many different carbons should we see in this molecule? 5. None of them are symmetrical. Also, now this is where carbon NMR is rather important. Chemical shift. A carbon-oxygen double bond carbon is typically at about 200. So I would expect to see this at about 200, and these others I would see between 0 and 50. So let's just take a look at that. Again, highlight, spectrum, generate carbon NMR. And pretty as you please, 4 between 0 and 50, 1 at about 210. That 210, it means either aldehyde or ketone. To me, the utility of carbon NMR for simple molecules is validating what you think it is. We can get everything we need from the Proton NMR, IR, and mass spec.
Excuse me.
So now that we feel good about our predictions, let's actually look and see if we can find some experimental spectra. Of course, I'm going to need to connect to the internet here. Do they have a wireless here?
Yeah, probably doesn't
It's
work that
Republic
well,
Open.
So, unfortunately, there's no experimental spectrum, but this is the process that I want you all to go through as you are solving. So now I think what we need to do is on this next screencast, we're going to do just the opposite. We're going to start with the data and end up proposing a structure.